All right, let's start. We are very happy to have Professor Lawrence Krauss from Case Western Reserve University here. Professor Krauss is, I think, mostly known to the wide public for his investigations of the physics of Star Trek. And before we start, let me mention that we have the questionnaires here, as usual. Everybody is encouraged to fill this out and send it back within 1 week. And only those people who are doing this will receive the copies of the transparencies as an incentive to fill it out. Please.
Okay, good. Well, let me apologize for the weird time that this began, but you all know why. I didn't have the heart to attend the last lecture that was in this auditorium. I figured it would be a performance I couldn't follow. But in any case, that's the reason it's been delayed. And I'm sorry. In any case, this was an extremely difficult lecture series to prepare for me because the topic is very broad, as you will see. And I tried to think of some coherent subtitle that would indicate exactly what I intend to do today. And the closest thing I could come up to was the following, which is, as all overviews are self-serving in some sense, but I'm going to pick and choose topics, as you will see, although in the first part of this lecture I will try and give an overview of the field so that you'll get some idea of the things I leave out. Now, there are two other things I wanted to mention. I wrote them down here to remind myself. The first is the weird time. This is 3 lectures of an hour and 15 minutes. Actually, it's an hour and 18 minutes. It was supposed to be 4 lectures of an hour, but there were problems with this room, so we changed it. And that would, of course, if you do the mathematics, you will find out that that's 3-hour lectures of an hour and 20 minutes. However, I reduced the length of time of the lectures by 2.5%. So it's 1 hour and 18 minutes. The other thing is, who is this lecture for? I always try to think of an audience when I prepare a lecture. And this lecture is for an intelligent experimental graduate student, or Jack Steinberger, who put together. And so I noticed that there are several experts in the audience, and that's all right, because I plan to drive them away quickly. First, I've studiously avoided any reference to any of the experts in this room, so they will become sufficiently disgusted that they will walk out early on. Okay, let me first give a general definition of particle astrophysics. I want to begin very broadly. And before I focus, there are 2 sort of directions of particle astrophysics. The first is to effort to use the observables of astrophysics and cosmology. The observables, again, I'm talking to, as if I'm talking to experimentalists, and I think I want to concentrate on observables wherever possible. And to use those to constrain the fundamental parameters of particle physics, as I'll show you. The other side of the coin is to use the results of particle physics to understand the origin and evolution of astrophysical systems, which cannot be understood otherwise. Those include, among other things, stars, galaxies, and the universe itself. The purpose being then to use the universe, rather than a terrestrial laboratory, as both an accelerator, produce particles, as a target to detect them, and as a laboratory itself in which to do the experiments. I tried to think of the earliest example I could think of particle astrophysics in what I would call the modern way of thinking. And the earliest I could come up with was from Descartes, from his book Principia Philosophiae in 1644. This, as many of you may recognize, is Descartes' cosmogony. It's his picture of the early universe. And he pictured the early universe as a bubbling, boiling, turbulent series of eddies, vortices. Why? Because of what we now call the conservation of momentum. Namely, he had a different way of putting it. He said motion is given by God. And so therefore, if the planets are moving, and stars are moving potentially, or at least the planets are, then they had to have been moving at the beginning. And the way to make them move is to have a turbulent vortex. And these planets will move around this vortex, and you will have turbulent flow all around. Now, that was an interesting idea, and it was based on a fundamental physics principle, conservation of momentum, which he invented in principle. And it predicted, he claimed, these vortices. But the other aspect of it, which is relevant for particle physics at the time, and right until the beginning of this century, is it was the first explanation of the origin of the ether. Namely, he argued that at the interstices here, between where the eddies ground against each other, matter would be ground into a finer and finer material until it would be ground into something so fine that you couldn't detect it directly, and that would move out throughout the universe and be the ether, which of course was needed for the propagation of light, among other things. So here you have everything we would describe in modern particle astrophysics, some fundamental principle predicting some phenomenon in the early universe, which then predicts something which in principle explains what we can see, and also may involve a new type of elementary particle. Okay? And we will see this reoccur many times. In fact, we'll see the same figure reoccur later on when I talk about monopoles. So that's the idea. Now, before I get to the promotion part of the program, where I want to try and indicate to you why particle astrophysics is worth considering doing, I want to give you several warnings. And these are very important warnings, in my opinion, for any particle physicist in particular thinking about these things. The first is that, as I like to remember, it's kind of rare nowadays, that physics is an empirical science. And therefore, one has to wonder about what the empirical data is in particle astrophysics that you're dealing with. And as I was thinking about this, the other week, I actually turned on my computer from back home, which has one of these operating systems that gives you a stupid expression at the very beginning whenever you log on. But on last Sunday, I logged on and I got this, and it really epitomized for me some of the problems that we're going to encounter when we look at this. I'll read it for you. It's Veliland's laws of experimentation. 1. If reproducibility may be a problem, conduct the test only once. We will see this in many cases. In particular, one of the big problems in facing cosmology in particular is that one of the major tests was done only once, at least in our observable region of the universe itself. The next, if a straight line fit is required, obtain only 2 data points. Again, we will see that coming back to haunt us over and over again when we extrapolate wildly. And one is driven to that by the most important warning I can give people, and it never ceases to amaze me how significant this fact is, that observations are different than experiments. And we cannot treat, therefore, the constraints from particle astrophysics, in my opinion, the same as we can treat the constraints from experiment, precisely because these constraints are based on observations which are not controlled, and the dominant errors are not controllable. In fact, often the dominant errors are not knowable. So we have to be very, very careful when we claim something is ruled out in particle astrophysics. And this is a fundamental limitation, and it's a limitation I believe we'll never be able to get around, and it's one of the many limitations I think that, in my experience, when constraints on elementary particles have been derived in the past, numbers of neutrinos, etc. Many particle physicists took these with a grain of salt, I think, precisely for this idea, that if one felt that there might be some fundamental aspect that would obviate the constraint. And we'll see that happen. And so you might wonder then, given those fundamental limitations, and they are profound, and I don't want to minimize them, why at all we should even consider particle astrophysics as a way to constrain particle physics, and why young experimentalists might want to even consider going into this field, and even theorists too. The answer, of course, is astrophysics envy. And I want to explain it to you in a number of different ways. Again, in the kind of language I think that's relevant for an accelerator physicist. The first bit of envy has to do with energy. So I have a scale of energy versus center of mass energy versus time, and I somewhere here have added on an approximate history of accelerator physics and discoveries and energies, going from roughly every 10 years or so, from sort of the important experiments on QCD in the 70s, discovery of the W and Z in the mid-80s, and discovery of the top in the mid-90s. Luckily, I was able to, of course, plug each major. So this was, I could talk about SLAC and BNL, CERN, and Fermilab, and therefore show no bias. And the question, of course, is in 2005, in the next 10 years, the LHC is supposed to turn on. Fine. You notice the curve is starting to dip a little bit, and the question, of course, is what will happen after that point? Will it continue to go up, or will it go down, or will it stop? Even if it goes up at the same slope, one is limited. Compare this, of course, to what one gets from astrophysics. The kind of energies which are accessible to measuring particle physics parameters are, of course, unlimited. And from physics, which was well understood in the 70s, from Big Bang nucleosynthesis, one can constrain particle physics certainly up to the GeV range and well beyond that, as I will describe probably in the third lecture. Again, from the supernova, 1987, one, as you'll see in the second lecture, one can constrain physics well up, and from supernovae in general, well up to at least 10 to the 6th GeV, if not higher. And now from high-energy cosmic rays, we are now learning that cosmic rays go up to at least 10 to the 20th electron volts, if not higher. And they may or may not be relevant to our understanding of physics at that scale. Of course, that's just the present universe. The universe, as a function of time, goes to arbitrarily high energy as one goes back to arbitrarily early times. And to the extent that one can find remnants of each of these eras in energy, one can probe physics at a scale which is clear we will never get in the lifetime of anyone in this room at an accelerator in a terrestrial laboratory. So the energies are way beyond those which even your grandchildren will be able to use at accelerators. So that's one of the reasons people are driven to that. Another is luminosity. I tried to work out the luminosity of CERN, and I'm hoping I got it right. But anyway, I took the average beam intensity and worked out the optimal case of a beam going for a full year or so. And at best, it seemed to me that the LEP beams were something like 10 to the 15th ergs per second, which is a large number. But the point is, it's piddling compared to the luminosities the universe provides. The Earth, by the way, is a much more luminous source due to radioactive decays inside the Earth. 10 terawatts of energy is emitted continuously by the Earth's surface, which is conveniently very close to the amount of energy absorbed by the sun, which is one of the reasons why, as an aside, we have no proof that whether the Earth is cooling down or heating up as of yet. In any case, so that's 10 to the 20th ergs per second. The sun, of course, is 10 to the 33 ergs per second. An active galactic nuclei quasar might be something like 10 to the 45 ergs per second. And of course, a supernova emits during its brief second or so lifetime of important particles, namely neutrinos, 10 to the 53 ergs. So the luminosities accessible to us are way beyond anything we can do in a terrestrial accelerator. So I've done energy, luminosity. The last two particle physics parameters are cross-sections. If you think of the kind of cross-sections you can propose so that the mean free path is 10 to the 9th times the size of a detector of a particle. If you think about it, I believe that current accelerators are limited to this range of cross-section sensitivity. The entire rest of the parameter space, however, is accessible to astrophysics. This is very important. Very small cross-sections are accessible because the targets, say the Earth, are big enough to have interactions for very small cross-sections. And that, of course, is one of the many reasons that neutrino astrophysics is such an important field. The target volumes Again, I think about something like 10 million Swiss francs will buy you something like 10 to the 5th tons of detector, whereas the sun is 10 to the 27th tons. Finally, the other thing that's very important is the size of the interaction region. At the LHC or at Brookhaven, one might be able to heat up regions of 1 cubic Fermi to maybe 100 MeV. But of course, in a supernova, one heats up to 100 MeV a region of something like 10 to the 19th cubic Fermi. And therefore, one can do experiments on regions which are entirely different than those that one can do in accelerators. I'm not being facetious. These are all very important things, and they're things that never will be accessible at accelerators, and therefore it would be foolish not to take advantage of them. Finally, and I put this because it is important for young people especially, there's sociology. The field is data-rich, unlike some fields. It is technology-driven. Each new probe, it depends on new technology, has made a new discovery. Every time a new detector comes online, new discoveries are made. It's kind of, it reminds one of the good old days in other areas. In one decade, the following equipment came on: the Hubble Space Telescope, COBE, the Sloan Digital Sky Survey. We're going to see the Cobra Sambra map, maps of the microwave background, which I'll presumably talk about in the last lecture. X-rays, antimatter, gravitational waves, high-resolution ground-based telescopes. All of these things are just coming online, and they're bringing a wealth of new data. The other thing that I think is particularly attractive for particle experimentalists is that the average size of a large experimental group is less than 20 PhDs, which is probably fewer than the Xerox contingent of Atlas. And the last thing is that the techniques of elementary particle physics work. The best example I can think of is the Macho experiment, which I will refer to a little bit later today, I hope, involving gravitational lensing, which was an experiment that requires data taking and analysis something like 10 to 100 gigabytes per day at least. And that was daunting enough that it wasn't something that conventional astronomers would have considered 10 years ago. The first people to realize that they could handle that easily were a series of particle experimentalists who got into that field. And it is now common, and it's now done every day. And so the techniques that particle experimentalists bring are extremely useful and will and enhance the field. Okay, so that's the reason to consider doing particle astrophysics or even talking about it. Let me just do two transparencies of an overview of what are the relevant observables before I then get on to the actual content of this lecture. But I felt that this was important enough to do that I didn't mind spending 15 minutes on it. The playing ground of particle astrophysics involves at least the following observables, each of which I will try and touch on in these three lectures. The mass density of the universe, the age of the universe, coming from two different ways, measuring star ages and measuring the expansion rate of the universe. The fluctuations in matter, the distribution of matter in the universe, the distribution of radiation in the universe, the ratio of baryons to photons in the universe, the number density of other elements in the universe. These are all observables. The luminosity in the electromagnetic spectrum of the sun, the luminosity in the neutrinos of the sun, luminosity in the electromagnetic spectrum of supernovae, of neutrinos and supernovae, the luminosity in the X-ray band, luminosity in cosmic rays, luminosity in dark matter, and the list goes on. Those are the kind of observables one will think about, and it is amazing how much you can get out of each one. In fact, my entire lecture this morning, as I will show you in a second, will deal with the first observable. The kind of particle physics parameters one would like to constrain, after all, are particle masses, lifetimes, cross-sections, quantum numbers, mixing, symmetries, forces, topology, species, etc. And I found in old conference proceedings where I looked at this for neutrinos, but it works equally well here. I got tired. The connections between each of these things is remarkable. Each of these things constrains a wealth of these things, as I'll try and show you. And obviously, in three lectures of this type, I cannot do justice to this, so I will pick and choose. That's one overview. The other, I think, is important to think about. And again, I actually dug up this was a trip down memory lane. When I was preparing this, I was asked to give this talk after I came here, so of course I didn't have any of my now normal transparencies. So I looked up an old conference proceedings, which I hadn't seen in a long time, 10 years ago, in a conference in Berkeley. I prepared this, and I'm amazed I spent the amount of time I did doing that, but it's nice to see it. This is the grand unified neutrino spectrum. This is an estimate of the flux, the appropriately weighted flux, given that weak interactions sort of go as E squared. I've weighted the flux by an E squared to appropriately weight the detectability of neutrinos. And this gives you an idea of the sources of just neutrinos in the universe, coming from the cosmic microwave background neutrinos. If they're massless, cosmic microwave background neutrinos, if they were, say, 30 eV, that's probably now people would want to see 2 eV, which would be somewhere around there, as I'll show you. WIMP neutrinos, which at that time were possible, as I'll show you now, are impossible. So there has been some progress. Solar neutrinos, terrestrial antineutrinos, because the Earth radiates in radioactivity, it's a source of antineutrinos. And in certain parts of the spectrum even produces a higher flux at the surface of the Earth in antineutrinos than the Sun does in neutrinos. Atmospheric neutrinos, cosmic ray neutrinos, neutrinos potentially from WIMP annihilations in the Sun, as I'll talk about, and then to compare them to terrestrial sources, such as reactor neutrinos at 10 meters, LAMP neutrinos, and I even put CERN collider neutrinos here. There's a spectrum here of things to be discovered just in neutrinos, which are remarkable. Of these, only 2 or 3 of those peaks have been seen. In fact, let me think about the statement. I think maybe only 2 of those things have been seen. Well, let me just add on to that. That's what I wanted to do here, just to indicate the relevant photon spectrum, which is another area which we want to investigate. A very important area, which we'll see, is, of course, the cosmic microwave background radiation. Above that, there's a peak of infrared radiation from rescattered light. There's also a continuum background of extragalactic starlight integrated from all of the stars in the universe that gets absorbed and downscattered in the high infrared. And then, of course, there's the Sun, which is a non-trivial source of information in particle astrophysics and has a big bump, as it should be. The X-ray background, and then, since gamma rays and cosmic rays are very close, I decided to just, for completeness, add to this the grand unified particle spectrum. Now, I've talked neutrinos, photons. Let me add the cosmic ray background, which is very important and of great interest, especially up in this range right now. And of course, when one talks about particles, one can add to this a zoo of particles that haven't been seen. The one thing I realize I forgot to put on here now is the gravitational wave background, which we know from the Big Bang is here, and there may be a continuum here. But here's an example of a peak which may exist, for example, if axions are dark matter. So the spectrum of energy and particle type is quite remarkable. And very few of these, some of these peaks have been seen clearly in the photons, but this is the playing ground, the real playing ground of all of the data I'm going to talk about, each one of these peaks. And I thought it might be nice just for completeness and reference, in case any of you keep the transparencies, to have this kind of spectrum, to see what really the field is all about and what the sources are. Okay, that's my overview. Now let me just talk about what I'm going to do today and in the rest of the lectures. I've now completed the overview in about the time I thought it would take, thankfully. And the rest of this lecture will be on the mass density of the universe. The reason being that it is incredibly rich, and it's a prototype. It is I tried to think of the best example of the connection between particle physics and astrophysics, and the connection between accelerator physics and non-accelerator physics. I want to talk about the observables of dark matter, the observables of the mass density, the reason why we believe there's dark matter in the universe, the constraints on particles, how we can detect them, and some object lessons. And that's what I'll be doing in the next 50 minutes to an hour, actually 53 minutes. In day 2, I want to deal with stars and stellar physics, and I want to talk about 3 different sets of constraints. I'll spend a fair amount of time talking about the age of the universe as determined by the age of stars in the universe. I'll show how stars can then be used, and of course this is very important, it'll come back later on in the third lecture, to talk about the limits on various particles from axions and monopoles and to some extent neutrinos coming from stellar evolution. And then finally the two most standard examples of stellar physics that are used to constrain particle physics, the solar neutrino problem and the issue of supernova neutrinos and where we're going there. In the last lecture, depending upon how much of these I get done here, I want to talk about the galaxy and the universe, and I will talk about galaxies and their distribution, their mass and their baryon fraction, and talk about how important that is. And then I want to talk about two aspects of the universe itself. First of all, the primordial abundance of elements and Big Bang nucleosynthesis, which I'll leave till the end rather than the beginning, just because it fits better here, I think. And the issue of large-scale structure, which will lead me to conclude with the cosmic microwave background. And then I want to really conclude with what I think are the major challenges and problems in the field. So now you know what's going on and whether or not you want to attend the rest. Okay. I'm going to be, as I say, fairly pedantic. It's certainly the beginning of these lectures, and I apologize for those people for whom this is too pedantic. But I want to remind you that why the mass density of the universe is important, specifically because we are lucky that the universe happens to be isotropic and homogeneous. We know it's isotropic by looking around in many ways, and so let me just show you some pictures that come from observations. Looking at galaxies on large scales. Here are a lot of galaxies. And there are a few lumps, but they're more or less the same number of galaxies in all directions. This is one. This is a Lick sample. One can look at galaxies in the infrared, and a very important source of cosmological information came from the IRAS satellite. And again, you look out over this is some plane looking out in all directions that's mapped onto a plane like this, so a surface in a two-dimensional surface that's mapped on to this flat plane. And you see again uniformity. But these pale in comparison to the most recent data, which is really beautiful. I hope it comes out on this figure. I downloaded. From the APM galaxy survey of 2 million galaxies in a large swatch of the sky. Well, as I thought, it might be too dim. But you can look at the transparencies. If you look at that, there are 2 million, well, there are not quite 2 million dots there, but there are dots of increasing intensity which show the intensity of galaxies. But if you were to look at this transparency in a dark room, you'd see it is a space-filling region. There are galaxies everywhere and it's uniform. It's really a beautiful picture, and you should come look up at it afterwards. Of course, so there's uniformity. Of course, that's just in matter. We know, and I didn't have this picture to bring with me, so I reproduced it myself. I drew it. I hope you don't mind. This is the Kolbe picture of the universe with the temperature of 1 electron volt. This is also the surface of the microwave background viewed in all directions, projected on a plane, and I'll talk more about that in the third lecture. And unfortunately, the only picture I had was one that had lumps in it. But that's the most recent. The most important picture from Kolbe is the one that has no lumps in it. If you look at it, the original pictures where color represented temperature, they were uniform. Usually pink, like a map of Canada if you live in the United States. Canada's always a pink blob up there. And since I grew up in Canada, I was particularly attuned to that. But this is uniform to at least one part, better than 1 part in 10,000 across the sky. So isotropy is clearly true. Homogeneity is measured a number of different ways, and I just want to remind you of how it's done, because it's not normally talked about. It's quite simple, really, and like many things, Hubble was the first one to really apply this to the universe. The flux of stuff coming from a galaxy is the luminosity divided by 4 pi r squared. Let's assume for the moment all galaxies have a single luminosity. Okay? Then all things which appear brighter than a certain galaxy have to come from a distance that's less than r. And one can ask, what's the number, therefore, of galaxies which come in a region less than r? Well, it's the number density times the volume contained in a distance r. So that's 4 thirds pi r cubed times n, or it can be written this way. Writing r cubed in terms of L, one gets this. Now, one has to use one little bit of jargon which I hope one can forget after this point. but it's this ridiculous fact that astronomers measure luminosity in some inverse way. They talk about apparent magnitude, which is minus 2.5 log to the base 10 of the actual flux, plus some constant, which is irrelevant for this argument. And all that really matters here is that means that you can say the flux is proportional to 10 to the minus 0.4 power of the apparent magnitude. And therefore, this statement, if the density of galaxies is more or less uniform over this course, this statement is only true if n is a constant. Okay? And this statement translates into a number of galaxies with apparent magnitude less than m, goes like 10 to the 0.6 m. And it was already known early on in the 1920s that when you did that for stars in our galaxy, that law was violated because of course, our galaxy has an edge, and stars aren't distributed uniformly throughout space. This is a recent compilation from 1991 of this same curve, and the line is 10 to the 0.6 magnitudes, the prediction. And you see, it is roughly in agreement. There's some excesses due to clustering on a certain scale, but there's no clear edge necessarily up to here. So it's certainly out to large distances, the universe, as we've just seen, well, is isotropic and now is also homogeneous. Those are two important features, and they're so important I actually wanted to show you the data for them, which is why I did that. But they lead us to simple dynamics. So I will have two transparencies just to remind you of the dynamics of an expanding universe, which will be important for the mass density. Because of the fact that the universe is isotropic and homogeneous, what that really comes down to in terms of physics is that the metric of the universe can be written in terms of only one parameter that's important, one dimensionful parameter, the scale factor of the universe. That's all that matters. And one can write a metric, the standard FRW metric, where this is the only quantity which is relevant. And of course, because it's the only quantity that's relevant, it sets the entire scale for everything one does in cosmology. That sets the scale size of the universe, the dimensions. Well, from this metric, one can write Einstein's equations. In fact, you can do it using just Newtonian physics, but I decided I didn't want to do it here. But the important point is that all of the dynamics is codified in R, and one gets that R dot over R squared, which is R dot over R is what we call the Hubble constant, plus K over R squared, where K is the curvature of the universe, which is plus 1 if the universe is closed, 0 if it's flat, and minus 1 if it's open, is related to the mass density, the total density of the universe. That's one equation. The second equation, which is important, is just that just comes from energy conservation, that the change in work is related to the force, the pressure. The change in energy is related to the work done on the system. But because the matter pressure is 0, this is quite simply solved to find out that the energy density of matter goes down as 1 is over the volume of the universe, 1 over the cube of the radius. Radiation, on the other hand, because it has a non-zero pressure and therefore does work on the expansion, loses energy faster. And its energy density falls to R to the minus 4. They both come from just this simple energy conservation equation, which is one of Einstein's equations, but you don't need Einstein's equations to derive it. It's just energy conservation. Now, there are two important predictions that come from this that are very important, I think, anyway. The first is that if there exists one photon in the universe today, and looking at this overhead projector, we know that's true, then the energy density of radiation had to exceed the energy density of matter at early times. Because this goes as R to the minus 4, and this goes as R to the minus 3, and if you go back long enough, no matter how small this density is today, it will beat that density there, if you're willing to extrapolate to small enough R's. The second thing, which is equally important, is that as long as there's one particle of matter in the universe, which we know by looking around the room, the energy density of matter will always eventually overwhelm the energy density of radiation. We currently believe we are in an epoch where the energy density of matter dominates the energy density of radiation. In fact, there are strong constraints that tell us, in fact, that we are in such an epoch. Okay. From this important equation, one can simply define the quantity, the closure density, which is equal to this, implying this quantity is then 0, if that were the case. And its value, which we'll come back to several times, can be written in some obscure notation as 1.9 h squared times 10 to the minus 29 grams per centimeter cubed. In a more rational notation, 8h squared times 10 to the minus 47 GeV to the 4th power. Or in a mixed notation, h squared times 10 to the fourth eV per centimeter cubed. All of those are useful in different contexts to think about the energy density, the closure density of the universe. And of course, in this case, I've normalized h to be 100 kilometers per second per megaparsec times the Hubble fudge factor, little h, which currently, as I'll talk about in the next lecture, goes between 0 and 1. It normalized this way, and there's an h in here I forgot to put. If this were this is 9.8 times 10 to the 9th inverse years, and that should be for h normalized to be a half. I'm sorry. No, sorry. That's for h. That's for h equal 1. Okay. Well, given that, one simply defines the quantity omega, which is the actual density over the critical density, and then one can rewrite Einstein's equations in this, for the expansion of the universe in this form, which is that k over r squared equals 8 pi g over 3 rho critical times omega minus 1. And that tells us the future, because if omega is equal to 1, the curvature is clearly 0, and if omega is greater than 1, the curvature is positive and the universe will collapse. And if it's less than 1, the universe is open. So the entire content of modern cosmology, in some sense, is to measure this quantity. And how do we determine omega? Well, we can get an upper limit on omega in some sense from the fact that the universe is still expanding. When omega becomes very large, the universe starts to collapse. Like any distribution of matter, when it gets dense enough, it starts to collapse under its own gravitational strength. And therefore, in fact, one could put an upper limit on omega that it's of order 1. In fact, an upper limit is probably something like 2. Omega is less than something like 2. Clearly, to get a lower bound, one measures the luminous mass in the universe. And in the optical region, one can measure the luminosity density of the universe, and this is the number, the current number that I could find. It's 10 to the 8th solar luminosities per cubic megaparsec times little h, which enters everywhere because it sets the scale, the Hubble constant, which depends on r, sets the scale for everything in the universe, distance scales. And it's best to think, I read, that it's best to think of the error in an exponent here. Now, that's the luminosity density. The question is, what does that mass correspond to by looking in our galaxy and nearby galaxies and asking how much luminous material corresponds to how much massive material in both stars and hot gas. The best estimate is that the mass of luminous stuff is related to the mass to luminosity ratio of the sun as that the mass to luminosity ratio of galaxies, of the visible parts of galaxies, is 12, this is in the optical, times an error times h. Well, multiplying these two quantities together, one gets, and appropriately adding in quadrature the errors, one gets that the average energy density associated, mass density associated with luminous material is therefore 1.2 times 10 to the 9th solar masses per cubic megaparsec times some h squared times some uncertainty, which in this obscure set of units that I discussed earlier is 8 times 10 to the minus 32 grams per cubic centimeter. Now, given what I told you was the critical density, this tells us, therefore, that the omega in luminous material is 0.004 times some error. And the important thing here is there's no h, because there's an h squared in this, and then there's an h squared in the critical density, and therefore h drops out of this estimate. That's the energy, that's the mass density in everything we see in the universe. And this was one of the many things which 30 years ago almost led cosmologists to argue that the universe was open, because everything you could see led to a very small percentage of 1. Another way of thinking about this is that, and using the fact of the mass to light ratio of galaxies, is that to get a critical mass in a large enough region of the universe, one would need a mass to light ratio of 3,000 in units of the mass to light ratio of the sun times these quantities. This is a thing to remember later on when we want to ask if the universe is closed. But there's a loophole here, which I guess was not so obvious to early cosmologists who argued that the universe is open, and that is that this is only what you can see. Clearly, there's lots of stuff you cannot see. If I were to turn the lights out in this room, I would not be able to measure the mass in this room very effectively. Most of you don't shine. Some of you who work on accelerators and probably do, but in any case, how do you determine the rest? And the answer is quite simple. There's a noble tradition. You copy what was done earlier in physics. You weigh the universe. And I want to remind you, this is, again, old stuff, but I think it's important enough to get everyone on the same page in case some of you don't know this. Newton derived the law of gravity by the motion of planets around the sun, and in fact the moon around the earth. And he derived, and now that we know the law of gravity works, one gets the fact that the orbital velocity, circular orbital velocity of planets is related to gm over r. Cavendish, when he wrote his famous paper in 1798, measuring the gravitational constant, knew then, even then, that a sexy title is worth a lot. Readers are going to look at a paper and see whether they want to read it. And instead of calling the paper On the Strength of Gravity, if you look at that paper, you will discover it is called Weighing the Earth. The reason being, this was well known. This quantity was measured, and say for the moon, this quantity was measured and this quantity was measured. But until you knew G, you didn't know M. So he argued that, of course, being the first person to measure the strength of gravity, he was also, therefore, the first person to measure weigh the Earth. Well, it worked so well for him, we continue to copy it. We can not only use this principle to weigh the Earth, we can use it to weigh the sun, the galaxy, and the universe, and it actually works. Namely, inverting this, one gets the mass in a certain region is the orbital velocity, circular orbital velocity, times r over g. And I just want to remind you how well it works in our solar system, and then I want to look at galaxies. I got this information from a first-year astronomy textbook where you can get this stuff. This is the orbital velocity of the planets around the sun. And this is Newton's prediction. V squared goes like 1 over r. And of course, to weigh the sun, you take this predicting curve and you fit it to the data. And it is truly, I didn't fudge the data. Okay, I would have if it was necessary, but I didn't. And this is a remarkable agreement. It's truly remarkable. In fact, from this you get a measurement of the mass of the sun. In fact, it's worth mentioning, and it's in some sense particle astrophysics, that one could in principle use this technique to measure the mass of the sun to better than 1 part in a million. However, we cannot. The reason being that the fundamental quantity that's relevant here is g, the gravitational constant, and we do not know from fundamental microphysical measurements the gravitational constant to 1 part in a million. So the limitation in our ability to measure the mass of the sun is our ability to measure a terrestrial quantity, namely the strength of gravity, between two known masses. And it's rather interesting, because we in principle could even measure this better to 1 part than 1 part in a million. At the level of 1 part in a billion, interesting things happen. Now I want to remind you that it didn't have to be this way. If there were just a small amount of dust around the sun whose density fell off quite dramatically by the time it was at the Earth, but whose total integrated mass over the region of the Earth, say, would be something like the mass of the sun, then of course this curve would not be this curve, it would be this curve. Now, you wouldn't see this dust, and therefore it's very important. Newton was well known not just because he was brilliant, but because he was lucky. Because there could have easily been dust in the solar system which would have screwed up this relationship. In fact, had Kepler discovered this law for the motion of planets around the sun instead of this law, then Newton would have derived from this law a 1 over r law form for the law of gravity you can calculate, in which case he would have gone into full-time alchemy, because it wouldn't have worked. And so it's very important for the history of science that in fact this accident didn't happen, but it could have. There's no need for the agreement to have been as good as it is. In any case, one was emboldened by that agreement to try and weigh the galaxy exactly the same way. And in our own galaxy, when one does that, our sun is on the edge of the Milky Way galaxy. One can measure its orbital velocity, circular orbital velocity around the galaxy, and predict, given that we are at the edge of the luminous region of our galaxy, how objects which are further out, how they should fit this curve, and try and get a good measurement for the mass of the galaxy. And of course, what is well known is that as good as the agreement was for the sun, the agreement was equally bad for our galaxy. None of the objects that one tries to measure, globular clusters, large clouds, large Magellanic clouds, satellite galaxies, None of them follow this curve where the luminosity of our galaxy falls off outside the region of our sun, and therefore one might have imagined that the mass of our galaxy, by the way, if one does this to get the mass of our galaxy inside the sun, one finds, this is a prediction, from fitting that point, one gets a mass of our galaxy of 10 to the 11th solar masses, which is very spectacular because the luminosity of our galaxy is 10 to the 11th times the luminosity of the sun. So one would have thought everything should work, and one should be able to get a better mass estimate for a galaxy by fitting these points to this curve. Clearly they don't fit, but of course I prepared your minds for that. If there is an invisible component whose density falls off as 1 over r squared, then of course you can fit that. And I just want to show you, I think I want to show you, maybe I did in the last transparency, well, that in fact, one, not from just our own galaxy, but from all other galaxies. I just want to show you the standard data so you should see it at least once. One can measure in particular the 21 centimeter line of hydrogen gas which surrounds galaxies well outside the luminous region of stars. And there are many good examples. Here's one particularly good example of the rotation curve of galaxies. And this is the flat rotation curve that you saw for our own galaxy. And these are the different components, the disk and the gas. And in order to explain this rotation curve, one has to assume a halo whose density falls off as 1 over r squared. That's true. Here's another. Well, I guess I won't even bother to show that. There's a bunch of these. In fact, I just got off the web a very nice paper which actually argues that there's a universal rotation curve that fits all galaxy types. Spirals, ellipticals, dwarfs. This paper is by Salucci and Persic. It was on the web last week. And it claims that if you take this form as a function of luminosity of the galaxy, you can fit all rotation curves of all galaxies. This first piece goes to 0 for large distances, and the second piece goes to a constant, where x is r over some characteristic optical scale size. What this tells you is what I just said, is that the galaxy rotation curves go to a constant. And that implies, using Newton's law, that the mass continues to increase linearly with distance. And the density goes as 1 over r squared. And just to, by the way, to show you this is kind of quite remarkable. This is this one curve fit to galaxies of many different types, luminosities, etc. And the solid curve is the predicted rotation curve based on that form, and the data is the observations. It's kind of impressive. This is for spirals, I think. Yeah, this is for spiral galaxies. You can get a similar fit to mass increasing with radius for elliptical galaxies. So it's everywhere. Everywhere the observation is that the mass of galaxies increases linearly with radius, explained approximately by a density that falls off as 1 over r squared, and that clearly is not a density associated with anything visible, because the visible luminosity of galaxies, as you saw from those curves from the disk, and falls off, in fact, exponentially outside. Now, this is one of the things that makes this so interesting is a little bit of culture, is that, in fact, if you take a dissipationless system which is isotropic and has a temperature which is independent of radius, then one can write its pressure in terms of its density times its velocity dispersion, which is the RMS deviation from the mean, velocity squared. And then, assuming things are in hydrostatic equilibrium, namely that this pressure gradient responds to gravity, one can solve this equation. And what's rather nice is one gets, in fact, a density which at large distances falls off as 1 over r squared, where sigma is the velocity dispersion. You measure the mean square deviation of velocities of a large bunch of these systems, assume it's in particles in the system, assume it's in hydrostatic equilibrium, and you get a 1 over r squared distribution. So there's actually a physical prediction that you can explain this halo around galaxies by a dissipationless material that's basically what's called an isothermal sphere. And it tells you, by the way, that the measured circular velocity is related to the velocity dispersion by this 2 to the 1/2 power, which often comes in. Okay, but operationally what this tells us is that because mass increases its radius, the density of the overall mass of galaxies is, and this goes out to a distance for some galaxies 10 times as far as the optical radius, that the mass of those systems is at least 10 times as much, and some 20 times as much as the luminous mass. That tells you two things. First, that dark matter dominates galaxies. This is the unambiguous evidence from every galaxy we can see that dark matter dominates these systems, including our own. And it also tells us that omega in galaxies is much bigger than the 0.004, which was observed from luminous material. And it's somewhere between 0.04 and 0.1 at least, at a lower bound. So the density of mass in the universe, including dark matter, keeps increasing on a galaxy scale. What happens on larger scales? And the answer is, well, I'm not going to go into this in detail because it's a long subject and it's one of the things I'm going to try and skip, but let me just show you what you do, and it allows me a chance to show you a pretty Hubble picture. It's just gorgeous. This is the Hubble Deep Field. The point of this is that there are lots of galaxies out there wherever you look, and they're clustered, and some of these are at the same redshift, the nearby ones, and galaxies come in clusters that are sometimes gravitationally bound. And one could do the same trick in the dynamics of those gravitationally bound clusters of galaxies. And the clusters and superclusters are the largest coherent systems we know of in the universe of matter. And measuring the dynamics, which is really using the virial theorem, that the mean squared velocity squared is the average kinetic energy is related to the average potential energy of the system if it's in gravitational equilibrium. One derives estimates that are somewhere between 0.2 and 1 for omega on the largest scales we can see today. And I will talk about this more later in the last lecture probably. This number is controversial. 5 years ago, many people thought it was closer to 1 because the theoretical predilection is that this should be 1. Now many people would argue that the number is closer to 0.2 by reviewing the data, but it's somewhere in this range, and it's not much greater than 1, and it's not much less than 0.2. That's the important thing. Now, there are two other ways to measure these systems on large scales, and I want to mention them because they're both going to come back later on in this lecture series. In fact, one of them later on in this particular lecture, I hope, and that is gravitational lensing and X-ray measurements. They're direct probes of the mass of large systems. I have a one-page transparency on gravitational lensing, a quick summary. Einstein already knew, of course, that matter bends light. And in fact, you can calculate that the bend angle for a point mass, if you have an impact parameter b, is 4 gm over b. This means that you can draw a system with two impact parameters, which is solved by this configuration. And this is a gravitational lens. This means if the observer looks out, the observer will see two images of this distant object lensed by this intervening object, and one can in fact determine dramatically in terms of these distances this impact parameter. This will produce multiple images, or if this image is directly behind this, it'll produce a multiple image all the way around, or an Einstein ring. A point mass will produce a beautiful Einstein ring. Now, it also does other things. It magnifies this quantity. The sum of the intensity of these two images is bigger than the intensity one would have predicted for the original image. And of course, it goes, if F is basically related, if the Einstein ring is the scale here, with which you would see a ring around this object. It's a radius around this object where the actual ring would be located, and it's this size. Okay? It characterizes if the impact parameter is less than this, one will be able to get significant multiple imaging. One will also, it turns out, be able to get significant amplification. The number is here, and it's always bigger than 1. And as the impact parameter goes to 0, as f, the distance, this thing off the line of sight, divided by the size of the Einstein ring, as this goes to 0, this quantity can go to infinity. Okay? Because of this 1 over f here. So the amplification gets very large. Note, that's for a point mass. An isothermal sphere produces something very different, which is also quite interesting. It produces a constant bend angle. And that's rather amazing, because that means you can define a cross-section. Because of this constant bend angle, if this object is greater than a certain region, in fact the Einstein ring, off the line of sight, you will not get any multiple imaging, and if it's less than the Einstein ring off the line of sight, you will, and therefore you get a disk, literally a cross-section, inside of which, if the light ray traverses that trajectory, you are guaranteed to get multiple imaging, outside of which you will not. And of course, because of that cross-section, you can determine interesting things, as you can with any cross-section, probabilities. Well, when Einstein developed this, he said he didn't write it up for 20 years because he said it won't ever be observable. Well, the point is, it is observable, and it would be observable in this room. In fact, say that we were here an hour ago, and this person was in this room. If a black hole, a primordial black hole of sufficient mass, came in this room, anyone would be able to do the following observation. It would be fun. I was thinking about him and wondering about a black hole going through him recently when I looked at my paycheck. The point is that this is actually rigorously right. This is assuming a point mass traveling halfway between you and the object. Okay? And since this is an academic lecture series, I'm going to give some homework assignments before the next class. One of the homework assignments is to calculate the mass of this black hole. Okay? You can do it. But it produces an observable effect. And it would produce an observable effect in this room. It produces an observable effect in the universe. And we have some beautiful pictures of black holes thanks to this beautiful observatory, the Hubble Space Telescope. Okay? Here are some images which are relevant for determining the mass of individual systems and clusters of systems. Here is an intervening galaxy. I've blown it way up. And 4 images of a distant quasar. 4 very pretty images. And what's very good about 4 images like this is a typical pattern expected from an elliptical mass distribution. So you can invert this and, in fact, determine from the position and brightness of each of these 4 images, you get a completely constrained system, and you can infer the mass distribution contained here, its shape and total mass, and you can weigh the galaxy. And, of course, you find there's lots of dark matter. But you don't have to do it just for galaxies. There are some spectacular recent images from Hubble and others, but here's one example, where you can look at a cluster of galaxies. Here are nearby galaxies. And you can look at a faraway galaxy, which appears bluer here, and you see that the image of that faraway galaxy is multiply lensed. Okay? You see many copies of it all around here from this distribution. It's amazingly beautiful. There's many examples of this, and I downloaded another image because I think it's sufficiently pretty. And what's very important about these things is, you see, the problem with estimating a mass of this system by using the virial theorem is you have to assume it's sort of spherical and isotropic. And maybe it isn't. But with this system, where you actually observe the images, you can do a direct inversion and determine the mass and distribution, as you can in this cluster of galaxies, which also images distant galaxies, as you can see here, forming almost an Einstein ring around this cluster. And you can therefore use these to measure the mass of clusters of galaxies. And that's one of the ways you get that mass estimate between 0.2 and 1. The other way to measure directly the mass of galaxies is to use X-rays. The galaxy cluster is dominated not by the galaxies you saw, but by hot gas between the galaxies. That hot gas radiates in the X-ray band. That is by far the dominant mass in those baryonic mass in those systems. Now, if you assume that gas is in hydrostatic equilibrium, namely its pressure, again, is governed, pressure density is related to this force of gravity, and that the gas and the matter is in dynamical equilibrium, you can basically, from measuring the temperature and luminosity of the X-ray gas, invert that directly and determine the potential that gas sits in. So if you do that, and if you have good enough measurements, and they're beginning to happen, where you can measure the temperature and luminosity of the X-ray gas as a function of radius, you can measure the total gravitational well that that gas sits in, which gives you the total mass. But of course, because you measure the temperature and luminosity of the gas itself, you also measure the mass of the gas. So the total mass gives you the mass-to-light ratio of the system. But measuring both of these tells you the baryonic to total mass of this system. That will become very important later in the third lecture. This estimate, basically looking at some systems, tells you the total mass is something like less than 23 times the baryonic mass of these systems. Tells you that omega cluster is somewhere between 0.2 and 0.3. So this puts an upper limit on the cluster densities, which is less than 1. But something I want to leave you with is that those two direct measures of the mass of the largest systems we know of in the universe are in disagreement. Namely, systematically, the total mass measured by gravitational lensing is larger than the total mass measured by X-rays. These are spectacular measurements, as I think you've seen. It gives you an over-constrained system which you can invert, and it's very believable that this measures the actual mass. It is quite likely, therefore, that this underestimates the mass, and it may do it for one of many reasons, but the simplest is that one assumed a spherical system in hydrostatic equilibrium, and if there's any clumpiness, any anisotropies in the system, any inhomogeneities, it's going to change that relationship. Okay? But it does at least give you a lower bound, if you wish, in the mass of these systems, which is relatively high. Okay, that's the observations. Now I want to spend the rest of the lecture on the particle physics. Okay. The question is, what is the dark matter in these systems? Well, the first answer would be that it's baryons, because, of course, we know they exist. The answer that we commonly come up with is no, that that density of baryons is not allowed by a series of cosmological arguments, which I'll give in the last lecture. I want to save something for later so that you have to come. But from Big Bang nucleosynthesis and galaxy formation at COBE, one can argue that baryons cannot make up this dark matter. It's very important. Each one of those things independently argues that baryons cannot be that dark matter. Of course, each one of them could be wrong. But this suggests that the dark matter is made of something else, and that suggests particle physics. Independently, it was discovered that elementary particles can exist in one of three configurations. They can either be born dark, achieve dark matterdom, or have dark matterdom thrust upon them. I'm not being facetious here because each of these has a candidate. And I want to spend the next 10 minutes or so describing how those candidates come about, and then I want to spend 10 minutes on the detection and end this lecture. Those which are born dark, two examples of those are neutrinos and magnetic monopoles. Those which achieve dark matterdom are WIMPs, and those which have dark matterdom thrust upon them are axions. All of these are legitimate candidates, and in particular, all of them were proposed independent of the dark matter issue, which is very important, I think. They weren't invented. I mean, WIMPs in some sense were invented, but then supersymmetry came along. But each of them has a real reason to exist, a particle physics problem that it addresses, independent of the issue of dark matter. Okay, let me start to rev up here. Okay, the first example is neutrinos. Each of these will give us a little piece of information which will be useful in the second lecture. Neutrinos are born dark and proud of it. Neutrinos have a weak interaction rate, which of course goes generally as the square of the energy in the center of mass of the system, or in a thermal system is the square of the temperature. And that means as the temperature goes to infinity, the cross-section becomes very high, and eventually the cross-section exceeds the expansion rate. As I'll show you later, that implies these systems are in thermal equilibrium. So for all temperatures greater than their mass, for as long as this is the case, they will have a thermal equilibrium distribution, and if the temperature is bigger than their mass, they'll basically be relativistic. And we know the distribution of relativistic particles. It's this. Okay? The energy density goes as the fourth power of the temperature. And for the total number of species in thermal equilibrium, this is the number of helicity degrees of freedom of bosons, this is the number of helicity degrees of fermions. Neutrinos, of course, fermions. Now, the weak interactions decouple at a temperature 2 MeV, which again I will show you later. That means up to that point, because they're in thermal equilibrium as are photons, their temperature is the same as photons. But once they decouple, their temperature need not be the same as the temperature of photons. In particular, for temperatures below the electron mass, electrons and positrons annihilate in the early universe because their distribution follows the Boltzmann distribution. Once the temperature is below their mass, it goes like e to the minus m over t, and eventually gets smaller and smaller and smaller. Well, because it happens in thermal equilibrium, the entropy during that process remains the same. And for all particles in thermal equilibrium before that process at a temperature of half an MeV, and after that process at a temperature of, say, 1/10 of an MeV when it's essentially finished, the entropy afterwards is the same as the entropy before. But the entropy before has more particles, electrons and positrons, in the radiation gas than afterwards. So the effect of these guys annihilating is to dump entropy into the photons and to increase the photon temperature. But the neutrinos have decoupled before that time. So their temperature just goes down as 1 over the scale size of the universe. And therefore you can argue from these numbers that the temperature of photons is 11/4 to the 1/3 times the temperature of neutrinos. Therefore, there exists a thermal background of neutrinos today, and we know its temperature, about 2 degrees. If they're massless, their energy density is just 4/11 to the 4/3 power times the energy density of photons. However, if they're massive, then their energy, if they're massive, then this becomes 4/11, the number density, times their mass, divided by the temperature of photons times the energy of photons. Now, given this simple fact and the fact that the cosmic white-ray background photons today are 10 to the minus 4th of critical density, one can just use this to say this quantity will equal 1 if the mass of the neutrino is 30 electron volts. And that's a very famous calculation done in 1975 or so by Krauss. And as you can see, the neutrinos did nothing there. They just existed. They just existed in thermal equilibrium. If they have a mass, they will be the dark matter today. The same is true for monopoles. If magnetic monopoles form during a phase transition in the early universe, and of course, where some fields get twisted up in the mass of the monopole, but the fields can't be coherent over any region larger than the horizon size. So you would at best expect 1 monopole per horizon volume. If that phase transition happens at 10 to the 14 GeV, you can do the calculation of how big the horizon size is, and you'll find out the number of monopoles over the entropy at that time is 10 to the minus 13. And you can also show, and John Preskill was the first to show this, that in fact if the number starts out this small, they will not annihilate. And therefore they are doomed to dominate the energy density of the universe severely because they're massive, very massive, and their energy density drops as r to the minus 3rd, whereas radiation drops as r to the minus 4th. And that number density is prohibitively large, and they will overclose the universe unless you get rid of them. So they will not only be dark matter, they will be drastically dark matter. They will end the universe well before we exist, unless you do something about them. Now, the next thing, and I want to spend most of my time on this because it's most relevant for accelerator bounds, is WIMPs. The prototype of a WIMP, although I'll eventually get to a neutralino broadly, is a massive neutrino. And the abundance of this was, of course, as we all know, dictated by the one who died so that we might be saved. I refer, of course, to Boltzmann. Boltzmann equation is the most important equation in astrophysics, if not in physics. Okay? And the Boltzmann equation governs almost every calculation I will show you in the course of the next few lectures. Okay, it governs the evolution of species. It tells you how the number density of a particle species relates depending upon its interactions. And in particular, for a particle in an expanding universe, it takes this form. The number density changes over time in a way related to the expansion rate of the universe and then related to the interactions it has, of course. And if two x particles can annihilate and produce something else, then the rate at which they will produce other things will be their cross-section times relative velocity in thermal equilibrium times the square of their number density. Okay? And one subtracts out from this their equilibrium number density. That means if, as we all know in thermal equilibrium, if the number is equal to the thermal equilibrium number density, and things are in thermal equilibrium, this term vanishes, And this will tell us, just from solving this, that the number density will fall as 1 over r cubed, as it's supposed to in an expanding universe when that term vanishes. However, when the interactions become small enough so that the equilibrium number density times the thermally average cross-section is less than this term, then the number density will start to depart from its equilibrium number density. And you can actually solve this, and it's again a homework assignment. It's kind of nice. You can actually put this in a beautiful form by, instead of doing this, rewriting dn dt in terms of dn d-temperature, and then dividing both sides by the entropy density of the universe, which depends as the cube of the temperature. And one can then get a beautiful formula for not the number density, but the ratio of the number density to the entropy, which is the quantity we generally care about in the universe. And that has this pretty form. And one can find that this number density will follow the equilibrium number density until the thermally average cross-section times the equilibrium number density is equal to h. And at that time, the equilibrium number density is e to the minus m over t. And after that time, essentially, with some small corrections, the number density of this particle will remain constant at its thermal number density at the time it decoupled. Now, this was first used for weak interactions, which, of course, for particles of mass m, for neutrinos of mass m, the thermally average cross-section for Dirac neutrinos is just the Fermi constant times mass squared, which is a constant. And you can do the calculation for weak interactions, and it's been done, and you find out that the decoupling temperature is about 1/20th of the mass. Here's some numbers that have been worked out. And as you increase the size of the cross-section, these particles remain in thermal equilibrium longer before they decouple. And as I say, for weak interactions, the number is about 1/20th. And that means that one could calculate the abundance of neutrinos as the abundance of photons times this quantity, e to the minus m over td, basically, times the mass of the neutrino over the temperature of photons. And this calculation was done by a number of people, but Dicus and Lee and Weinberg. And one found that a 2 GeV neutrino would be the dark matter. Note, because the cross-section increases as the square of the mass, the cross-section increases, therefore, as the mass increases, Td over m neutrino decreases, and the number density of neutrinos decreases. This is the first time, we'll see this happen again in a moment, where this non-intuitive thing happens. You increase the mass of a particle, and its remnant energy density decreases. But it's true for Dirac neutrinos. Now, that's not just true, of course, for Dirac neutrinos, it's true for supersymmetric particles, as was quickly recognized. Because the mass of the lightest supersymmetric particle in the standard, minimal standard model, well, it's varied as experiments has continued to rule it out. It started out when I started doing this at 1 GeV, and now it's at 20 GeV or so, depending upon what you see the bounds in LEP 1.5. But the intermediate particles involved in the interaction are of order the weak scale. And therefore, these particles have interactions, self-interactions of order the weak scale. Their masses of order GeV. They are perfect dark matter WIMP candidates. And one can calculate, and I'll show you pictures eventually, for the abundance of lightest supersymmetric particles. But this exact same calculation suggests that their number densities gives an omega, which is between 1/100th and 1. And I want to give you some caveats. This is a more complicated calculation than for neutrinos. First of all, this is a calculation that was true for Dirac particles, but for Majorana particles, which lightest supersymmetric particles invariably are, the cross-section is not a constant, but in fact depends upon temperature, and is much less efficient at annihilating. There are many channels, and there are many degeneracies that make this much more complicated. And as I say now, when these calculations were originally done, the mass of the lightest supersymmetric particle might have been of order 1. It's now of order 20. And the regime of minimal standard supersymmetric standard model, or whatever you want to call it, too many S's, minimal supersymmetric standard model, which produces a viable matter density, is still there, but that parameter space is decreasing with time as experiments continue to not find supersymmetry. This is the only first principles mandated dark matter particle, as far as I know. Namely, these scales really come from particle physics, and they really produce dark matter. I'm going to go till about 1:07 today, just so you know. The last particle I want to remind you of, which is dark matter, and it's a very different production mechanism than the type I've talked about, is an axion, which is not produced thermally. Axions, of course, are, I'm not going to give you a complete review.